You can begin anytime.
Okay, good. So, hi everyone. Welcome to the session on information theoretic crypto and the idealized models. I'm Anat, and I will be chairing this session with Muhammad. And the first talk is about coupling of random systems, and David will give the talk.
Thanks for the introduction. So I'm presenting our paper, Coupling of Random Systems. And I want to start by giving a short motivation and explain what we mean when we say random system. So a random system is an interactive object that operates in rounds. And in each round I, you can ask a query and you get the response. So you ask a query xi, you get a response yi. And moreover, each round can depend on the previous rounds, and the system is probabilistic. So the outputs can be random. Okay. And what we mean when we say random system is really the behavior of this object as it is observable from the outside when interacting with it. This is completely independent of how the behavior is implemented. So this is independent of how you would implement it with, say, pseudocode or any kind of programming language. And in particular, it is independent of any computational model. Okay, we only talk about the behavior. So one way to characterize such a random system is by a sequence of conditional probability distributions that this has been done in previous work. And I won't discuss this here. But this is one way to do it. So a typical example of a random system is say, a uniform random function R from x to y. So this is the random system that for every query x that you're asking, you receive a uniform and independent random value y from this set here. And if you ask the same query twice, you get back the same response. Okay, and analogously, you can understand a uniform random permutation as a random system. Now, the point is that many statements appearing in the cryptographic literature are in fact statements about random systems. They would maybe usually not be expressed in such a language, but they are in fact statements about random systems. So for example, a well-known URP-URF switching lemma that we all know is in fact a statement about these two random systems, R and P, and about their indistinguishability in the information theoretic setting. Okay. Now, since this object is everywhere, essentially since random systems are everywhere, we want to understand them better, and thus our main contribution is a new simple theory of random systems. And we then show within this simple theory a new, what we call, coupling theorem of random systems that characterizes essentially the indistinguishability of two random systems. And then we use this kind of coupling theorem in a last part to show new indistinguishability amplification results. So I want to start by explaining sort of what the system theory is built on. Essentially, everything is built on what we call a deterministic discrete system, or a DDS. So this is the most simple deterministic case, and we see here just pictorially the four possible single query deterministic system on bits. So if the alphabet are bits, then you have four possible single query systems. So for example, here the system flip is the system that flips your bit. You have one query. If you input 0, you get 1. If you input 1, you get 0. Okay. And more generally, if you can have more queries, it would be, you get deeper trees somehow. This is depth 1, only one query, okay? But now, of course, we want to have probabilistic systems, and the most simple way to get it is just to say, okay, a probabilistic discrete system is just a probability distribution over deterministic discrete systems, over DDS. Okay, so for example, you can take these four DDS, these deterministic systems, and you can take a uniform distribution over these systems, right? And then what you get is the random system that behaves like this. It's easy to see that whatever input you give, you get back a uniform random bit. Okay, you input 0, you get 0 or 1 with uniform probability 1/2. Okay. But now we observe that when we do that, there are in fact different such distributions, or different PDS that behave identically. So in fact, you can put any alpha in the interval 0, 1/2 in here, and then you get the same random system, the same behavior. Okay, but since we want to talk about this behavior, we now introduce an equivalence relation. Say, okay, two PDS are equivalent if they behave equally. Okay, and then we say, well, a random system is just essentially an equivalence class of such PDS. So an equivalence class of distributions over deterministic systems. Okay. So now you can ask, well, if we want to talk about this behavior only, why did we introduce these equivalence classes, okay, and these distributions? Essentially, a nice thing that you get when you do that is that you can now lift statements definitions and statements and properties that we know from probability theory and probability distributions. You can lift them to the level of random systems, since these are now the probability distributions over systems, but this will not matter so much. Then you can lift them to random systems. Okay, and then we do this for a distance. We say, okay, we know how to measure the distance of two probability distributions. It's just a statistical distance. It's a meaningful way to measure the distance of probability distributions. So we lift this distance, the statistical distance, to random systems and say, we just take these two equivalence classes, these two sets of PDS, and we take the infimum statistical distance over all pairs that you can take. So this is essentially the minimum distance of these two sets, okay? And now you can ask, well, but we know how to measure the distance of two systems. We mean the distinguishing advantage. Distinguisher interacts with these objects and tries to guess which one it is. This is how we classically do it. And in information theoretic setting, we take the supremum distinguishing advantage over all distinguishers. This is what we know and what we usually do. And you can ask, well, how are these two things related? And we have a theorem that says, well, they coincide. This is the same thing. Okay? In particular, there exist always two PDS that have statistical distance exactly corresponding to the optimal information theoretic distinguishing advantage. Somehow looks like this. Okay, and now you can say, okay, it's statistical distance. We know there's a well-known coupling interpretation of the statistical distance. You can plug this in, and you immediately get the result that says you can think of two systems, S and T, that have distinguishing advantage, optimal distinguishing advantage epsilon, essentially as being not equal with probability epsilon, okay? In the sense that there exists a joint distribution, or what you call a coupling, that such that they are not equal, S and T are not equal with this probability. Okay, and now you can ask, well, what's the point of this? You can say, a nice thing about this is that you can now think of the closeness of two random systems, so two systems being epsilon close, as in terms of a failure event that happens with probability epsilon. You say with probability epsilon they are not equal, otherwise they are equal. And now this way of thinking is not completely new. What's new in this way of thinking, in the novelty that this theorem brings, is that you can now think of this failure event happening with probability epsilon as being sampled at the very beginning. It's essentially the system's randomness that we sample, and we can sample this event, the failure event, is it equal or not, at the very beginning of the interaction. So this means that you can argue about systems closeness without essentially arguing about the complexity of the interaction. Just at the very beginning, you sample this event, and then you know where you are. Are we equal or not? Okay. And then, so I have no time to show indistinguishability amplification results, but these are essentially results where you say, if you XOR two random functions, then their indistinguishability multiplies somehow, and then there is a correction factor. So this is a known theorem from Crypto 07. But we can prove this kind of results and actually generalize them. And the nice thing is now that in our proofs, we don't need to argue about the complicated interaction. These are a multi-query system, so you have complicated interaction. This does not even appear in the proof because we can sample this failure event in the very beginning. So the complexity of interaction is completely avoided in the proof. So for the details, you really need to read the paper. Yeah, thank you for listening.
Thanks, David. A nice talk. Let's see if we have.
I can stop the share. Yeah.
Yeah. Go on. So do we have?
I have a question in case others still are not asking one. So your paper gives a nice characterization of the optimal distinguishing between two interactive systems. I think the PR paper also had a different way to characterize it based on a bad event that happens, somehow a different way to look at it. Does yours give a simple proof of that paper as well, or? Can you subsume the results of that paper, or things still remain uncomparable? At least technically.
Essentially, the results from MPR07 essentially are immediately immediate consequences of this new of our new results. The new results are stronger in the sense that it's essentially about this interaction. So in MPR07, essentially it's in a similar way. There's a similar tight characterization of the optimal distinguishing advantage, but there it's in terms of an event that happens with probability.
Yes. Can you derive that as a corollary of your
this
characterization?
Is essentially, what we show is essentially a stronger version of that. Can be considered a stronger version of that in the sense that now this event somehow you can sample it even before the interaction begins. And in MPR07 they say essentially that no matter how you interact, at some point this event happens. It's a dynamic event somehow, and then but it happens only with probability at most epsilon, where epsilon is the optimal distinguishing advantage. And now we can say, well, we can sample this event in the beginning. So somehow this is can be considered a stronger version of MPR07. Yes.
Thank you so much.
Okay, good. So let's move to the next talk. Titled Towards Defeating Backdoored Random Oracles in Differentiability with Bounded Adaptivity, and Sogol will give the talk.
Thanks. So hi everyone, I'm Sogol, and this is a joint work with Yevgeny, Puya, and Stefano. So suppose we live in a terrible world where every hash function that we have and know is backdoored in a way that it can be covertly broken by a malicious designer. And in this setting, we want to know which security properties we can still potentially rely on. So this question was studied in a recent paper, which was called Combiners for Backdoored Random Oracles. And our results are also in their model, which is a model called the Backdoored Random Oracle model, or for short, BRO. And in the BRO model, a hash function is simply a random oracle, which comes together with an adversarial interface, which is called the backdoor oracle. And this backdoor oracle on input of a hash function f, in fact, any function, not hash function, it returns the output of f on the entire description of the hash function, which was a random oracle. So in this model, we give the adversary adaptive and unrestricted access to both of these interfaces, so the random oracle directly and also the backdoor oracle. But the thing is, with such a strong adversarial power, and when we have just one backdoor random oracle, no security is going to be possible because every property that we can think of can simply be broken by querying an appropriate function f to the backdoor oracle. However, it was luckily observed in the previous paper that security can indeed be revived by combining backdoored hash functions. So suppose we have not just h, which is backdoored, but also another hash function g, which is also backdoored, but it is independent from h. And in the original paper, they analyzed the XOR combiner, which is h of x XOR g of x, and they showed that you can, in the BRO model, actually achieve one-way security, PRG security, and also conjecturally collision resistance. Now, in this paper, we want to go beyond these single security properties, one-wayness, PRG, and collision resistance, and we ask the following question, which is whether we can have a combination of two backdoored random oracles, for instance, XOR, which actually behaves like a backdoor-free random oracle. And what we want here is the property of indifferentiability from a random oracle, which would ideally imply single-stage games such as one-wayness, PRG, etc. So our goal was then basically to show the existence of a simulator algorithm such that the adversary's interaction with the real world and the real interfaces look like an interaction with the simulated side. So this turned out to be very challenging, but what we could show was that this holds with a restriction on the adaptivity of the queries that the adversary makes. And this restriction was more precisely that it holds as long as the adversary's queries do not switch back and forth between the backdoor oracles more than a logarithmic number of times. And by the way, this also implies indifferentiability with auxiliary input or like two independent pre-processing on H and G. And another remark is that we also studied another combiner of three hash functions, which was a extractor-based combiner, and that in fact tolerated a linear adaptivity. So check out the paper for those results. Okay, now let's see how the simulation in the indifferentiability proof actually works. So simulating H and G without the backdoor oracles is very simple. So suppose we lazy sample H of 8 to be some value Y, and then we need to ensure consistency with the random oracle. Which means that we have to set G of 8 to Y XOR random oracle of 8. And the same principle goes for other points. So we always fix aligned points in H and G. And how would we deal with a backdoor query? So this boils down to basically figuring out given a backdoor response, which we call f of h, which points in h are effectively revealed because of that, and how the distribution of h changes. And for this, we rely on a lemma, which tells us that the ith backdoor response, f of h, leaks a lot of information only about a limited number of points in h. So this tells us that the min entropy of a bunch of points drops by a lot, and the simulator basically needs to fix all of them for h. So these are, let's call them pi points. So the simulator fixes them for h and also for g in a way that they are consistent with h and the random oracle. But this lemma also tells us that a little bit of information is leaked about the rest of H. And these are, in this picture, the light blue cells. And a bit more formally, we have that the min entropy of the light blue cells, and basically any combinations of them, drops by some factor delta I compared to the full entropy that they could potentially have. And these values delta and p depend on each other. And basically, the smaller delta you want, you have to basically fix more points. So the lemma that we use here is a refined variant of an existing lemma from Communication Complexity by Gauss et al. And I don't have time here to go into details of why we exactly get bounded adaptivity, but let me just mention that a potential improvement in this lemma which would fix considerably less points, may actually give us full indifferentiability. Okay, so obviously for more details and other results, check out the paper or the longer talk. Thank you very much for listening.
Any questions? I think, Anat, you're muted.
Yeah, so thanks for the talk. Yeah, sorry. A very kind of basic, maybe silly question. So the f, the leakage function, is it bounded in some way? Like, does it have short outputs or anything, or there is no restriction?
Yeah, that's a very good question. So the adversary makes those queries to the backdoor oracle. So if the adversary is bounded, it has to be able to basically process the outputs of F. So the outputs should have short lengths.
Right. So
Otherwise, it can be anything.
Right,
So
it can be anything, right?
Collisions. It can, yeah.
Yeah. Okay. Good. Thank you.
Etc.
Thanks. Any more questions?
I also have a quick question. So recently there was a work by Kang and Jeanri who showed that you can make actually computational assumptions even in the indifferentiability setting when we have idealized oracles. Do you think if we make some even very strong computational assumptions, there is a way to go for full result without bounded adaptivity? Because I'm assuming your results are all information theoretic and hold even for unbounded distinguishers, if I'm right.
Yeah. So
It might be something
I'm
that
not
you need to
familiar with
think
the work
about.
that you mentioned, but that would be a good
But yours
direction
is
to
information
investigate.
theoretic, I guess.
Yes.
Yeah. So you okay? So it's a stronger form.
And
Yeah, maybe a good question for future work then. But thank you for the talk.
thank you.
Yeah. Okay. So thanks for the talk, and let's move to the next talk on zero communication reductions. And okay, is Varun here? Okay, good. Okay, you can see your
Hi,
slides.
am I audible?
Yeah. So Varun will give the talk.
Okay.
Please.
So I'll start then. Hi, everyone. Thanks for joining this presentation on zero communication reductions. My name is Varun Narayanan, and this is a joint work with Manoj Prabhakaran and Vinod Prabhakaran. In cryptography, we use several information theoretic primitives like secret sharing, conditional disclosure of secrets or CDS, private simultaneous messages protocol or PSM, etc. These primitives are often simple to define and abstract out the essence of various cryptographic problems. In this talk, we introduce a novel information theoretic primitive called zero communication reductions, or ZCR for short. ZCR is a bare bones model of two-party secure computation. As we shall see, it ties together with various other primitives. Our contribution in this work is in three parts. First is definitional. We define ZCR with varying levels of security, with connections, and we show that it has connections to several other important cryptographic models. We obtain new upper bounds on complexity of PSM, CDS, and secure computation. All our bounds will be for statistical security. And all these bounds are derived via a construction of ZCR. This construction is in terms of what is called a relaxed partition for two-party function computation. This is a tool for deriving communication complexity lower bounds. We then rely on a result by Kernidis et al. From Fox 2012 to relate relaxed partition to information complexity of functions. In some cases, the upper bound we obtain this way yields an exponential improvement over all prior upper bounds. In the other direction, we also show that lower bounds on complexity of a secure variant of ZCR will yield lower bounds for secure computation. Lower bounds have known to be hard to obtain for secure computation. For OT complexity, the best known lower bound are due to Beamel and Malkin from TCC 2004. And since then, there have been no improvement. We can recover these linear lower bounds using the connection to secure ZCR. But more importantly, we exploit only some aspects of the complexity of a secure ZCR for this. By using a fuller notion of the complexity of this model, one can hope to significantly strengthen this lower bound. We capture this complexity measure linear algebraically as what we call the invertible rank of the matrix representation of a function. A superlinear bound on invertible invertible rank of a functions matrix would imply superlinear bound on its OT complexity. And this in turn will imply lower bounds for circuit complexity and PIR due to known connections. So we could think of this as a new cryptographically motivated approach for attacking important computational complexity questions. But the invertible rank itself is a purely linear algebraic definition. In the paper, we present a conjecture regarding the invertible rank that can be understood without knowing any cryptography. And we encourage everyone to check it out and try to prove or disprove this. Okay, now let me tell you what a zero communication reduction is. It's a really simple model for two-party secure computation, where, as the name suggests, the two parties do not communicate at all. Yeah, so in a zero communication reduction of a function f to a predicate phi, Alice and Bob have inputs, say x and y. Based on the input, each party locally produces a candidate output along with an input to the predicate phi. The candidate output of Alice over here is A, and her input to the predicate is U. We require that the predicate accepts with a minimum probability for all inputs. So this is the non-triviality condition. Additionally, the candidate outputs are required to be correct whenever the predicate decides to accept. This is the correctness condition. When the predicate accepts with probability at least 2 to the minus mu for all inputs, we'll call it a mu ZCR of the function f to a predicate phi. The smaller, we would like to have smaller values of mu. That would imply a better zero communication reduction as the predicate is accepted more often. ZCR definition can be strengthened with varying levels of security. We study ZCR, weakly secure ZCR, and strongly secure or simply secure ZCR. A ZCR has no notion of security, and it only needs to satisfy non-triviality and correctness conditions. Whereas the weak ZCR additionally requires that the inputs are hidden from an adversary who can see the decision of the predicate. Hence, the probability with which the predicate accepts must be the same for all inputs. In strongly secure ZCR, the adversary can also corrupt Alice or Bob. To ensure security against the corruption of Alice, for example, the view of Alice must be simulable. That is, for any input x and y, the joint distribution over the random variables r, u, and the decision of the predicate together, they must be simulable using only Alice's input and her correct output. So similarly, we will have a security requirement for Bob too. So this is the model. Please do take a look at the paper for more information. Thank you.
Okay, so thanks Varun for the talk. Do we have any questions? So just a quick question regarding that matrix conjecture, matrix related conjecture. How, like, does it look like anything that has previously been looked at in the literature, or does it look like something completely new? And they're like, what would your guess be like? Do you believe it's true that?
We believe it is true in the sense that, the conjecture is in terms of the truth table of this matrix. And what it boils down to is the following question, that can we give a lower bound for secure computation when all we need to guarantee is correctness, is security for a really low probability event in which we compute the correct answer. And otherwise we don't have any guarantee on the correctness, right? So this particular notion is, we can think of it like a partially secure protocol. And if we can show that the communication complexity is not hit really badly when we relax in this particular way, then we should be able to get a lower bound using this linear algebraic characterization. So does it look like something that has already been described? To the best of my knowledge, I have not seen this kind of a description before.
I see. Okay, thanks.
There is a question by Amos in the chat saying, what is the improved complexity of CDS and PSM protocols?
So we have upper bounds that are exponential in the information complexity of the function that is getting computed in the PSM, and information complexity of the predicate in the case of CDS. These are both in the statistically secure regime. Yeah.
I also have a quick question. I don't know if it's in the paper already or not, but I think your definition was for deterministic functionalities. Is there a version of zero communication reduction for randomized functionalities? Maybe it's
Yeah,
already done.
the definition as such is given for randomized
Got it.
functionalities. Here we have only described the deterministic one.
Got it. Thank you.
Okay.
Okay. No more questions, it seems, right? So thanks again, Varun, for the talk, and let's move to our next talk on titled Algebraic Distinguishers from discrete logarithms to decisional Uber assumptions. And Lior will give the talk.
All right, thank you. So can you see the slides okay?
Yes.
Great. So thank you for the introduction. As was said, I'm going to talk about algebraic distinguishers, or the decisional algebraic group model. And this is a joint work with Dio. So let's start by discussing the generic group model. So this is a very well-known and successful model that idealizes computations within algebraic groups, typically cyclic groups, but not exclusively. And generally speaking, it captures algorithms that do not exploit the representation of underlying group elements in any way. So this is typically captured by withholding the representation of group elements from the algorithms and somehow restricting their access to the group to abstractly performing the group operation and to check inequalities between two group elements. So for example, in the Schup's model, this is captured by replacing the representation of group elements with random encoding and outsourcing the group operation to an outside oracle, which performs the group operation for the algorithms. So, this generic group model, as I said, is very successful and it has many benefits. So for one, it captures a natural and wide class of algorithms, namely those that do not exploit the representation of group elements. And in particular, it also captures the best known attacks against discrete log-like problems in the elliptic curve groups. And more technically speaking, it also enables one to derive clean information theoretic lower bounds. And oftentimes, these are actually the only proofs of security that we know of. And other times, we start off with the proof of security in the generic group model, and later someone comes along and provides a group in the standard model based on some specific assumption. That being said, the generic group model is not without its limitations. So, for example, it induces, in some sense, no natural hierarchy of hardness. So any problem within the generic group model is either information theoretically hard or easy. You can think of ways to define a hierarchy of hardness, but this is somewhat, it's not, naturally inherent in the model. Obviously, not all algorithms within cyclic groups are generic, and we do know of some very important examples for fundamental problems in which we have non-generic algorithms, and on the other hand, we have generic lower bounds. And finally, it seems that withholding the concrete representation of group elements is a somewhat unrealistic assumption to make. So with these limitations in mind, Fuchs-Bauer-Kiltz and Loss introduced the algebraic group model. So this is a model which lies between the standard model and the generic group model. So it's more restrictive than the standard model. It assumes more, but it still assumes significantly less than the GGM, than the generic group model. And the key idea of Fuchs-Bauer et al. Is to distill one key algebraic feature of generic algorithms that is often used in proofs, while significantly weakening or getting rid of the remaining assumptions made by the GGM. So concretely, algebraic algorithms within the model of Fuchs-Bauer et al. Can use the representation of group elements in any way they see fit, under the condition that whenever an algebraic algorithm outputs a group element, it must also produce alongside it some sort of an algebraic explanation for how this group element was computed. So in more detail, let G be a group of prime order P. We have the algebraic algorithm, let's call it A. It gets L group elements as input, and it outputs a group element Y. So when A outputs a group element Y, it should also output this algebraic explanation W, which is a vector of elements in ZP, which describes how Y was computed in the basis of previously seen group elements. So concretely, Y is the product of xi raised to the wi for I, which goes from 1 to n. So I should say that this is inspired by earlier works which considered algebraic reductions rather than algebraic adversaries. And as an example, Fuchs-Bauer et al. Show that within their model, breaking the computational Diffie-Hellman assumption is equivalent to computing discrete logarithms in the group. Okay, so this is a result concerning the computational Diffie-Hellman assumption. And one may ask, what about the decisional Diffie-Hellman assumption or the DDH assumption? So here the adversary has to distinguish between two distributions. So we get a generator G, G to the X and G to the Y for uniformly chosen X and Y, and either G to the XY or G to the Z, and needs to decide which of the two distributions was used in order to sample the input. So let's say that we have some algebraic algorithm that tries to solve this problem. So this algorithm outputs a decision bit B, which is either 0 and 1, indicating which of the two distributions A thinks the input came from. So in particular, this algorithm A outputs no group elements, only a decision bit. And hence, in this case, the model of Fuchs-Bauer et al., the AGM, coincides with the standard model. It provides no additional power to reason about the security of the DDH assumption beyond that which we have in the standard model. And it's not hard to see that this kind of limitation is inherent for any problem in which the adversary does not output any group elements. And in particular, this includes all non-interactive decision problems. That is, problems in which the adversary has to distinguish between two a priori fixed distributions. Okay, so with that in mind, what we show in the paper, so first of all, we present the decisional algebraic group model, or the DAGM. This is a generalization of the algebraic group model of Fuchs-Bauer et al. That enables one to reason about algebraic distinguishers or decision problems, such as the DDH problem. So obviously, in order to do so, we need to strengthen the model of Fuchs-Bauer et al. But I would argue that what we do, what we offer is a reasonable strengthening of the AGM, in that our model still lies between the GGM and the standard model. And namely, it allows adversaries to use the representation of group elements in any way they see fit. We also consider extensions to multilinear groups. And within the model, we consider strong decisional assumptions. And we show that breaking them algebraically is hard if the discrete logarithm problem is hard in the group or some variant thereof. So concretely, we show that the discrete logarithm assumption in our model implies the DDH assumption. We also generalize this result in order to show that the decisional k-linear problem of Shaham holds even in k-linear groups. And we show that the Q discrete logarithm problem, which is a higher order variant of the discrete logarithm problem, implies the decisional Uber assumption of Bonnet, Boyan, and Go in bilinear groups. So I'll conclude with simply, throwing the model at you because we don't have time to do more than that. So what do we require of algorithms within our model? So let's say that we have some distinguisher A, it gets L input elements and outputs a decision bit. What we require is that alongside this bit, A also outputs some sort of algebraic explanation vector W. And we make two requirements regarding this W. So first of all, it has to induce some linear zero testing the exponent, which is passed by the input elements. So concretely, the product of xi raised to the wi has to be 1, or the identity element in the group. And obviously, this can be satisfied trivially by simply outputting w, which is the old zero vector. So we have some non-triviality requirement, which is that for any two distributions, if A distinguishes between them with advantage epsilon in time t, then there exists some bit b, such that when A is invoked on an input drawn from db, then with high probability, some probability which is a function of epsilon and t, this W induces some sort of a good zero test for distinguishing between the two distributions. So we have all kinds of ways to define what is good in the paper. We choose one for reductions, and you can see the paper for more details on that. Okay, so with that, I will conclude, and thank you for listening.
Thank you. Thanks for the talk.
Sure.
Do we have questions?
Are there any surprises in a sense that do we have examples where I guess the new model captures strictly more than a generic group model? I don't know, some Jacobi symbols, I don't know, something like that.
Nothing that I can, nothing that comes to mind right now. I'll have to think about it. We don't have anything in the paper.
And in terms of just like a warm and fuzzy feeling, is working in this model equally, well, I don't want to say easy, it's only easy in retrospect. How does it compare working in, I guess, like Schup's model or whatever, the original model, generic group model? Is it significantly different or a lot of similarities?
So it is different. It is different in the sense that typically what you do in the generic group model, like in Schup's model, is the computation induces some linear relation, and you can sample the input elements at the end, and then reason about what's the probability that this linear relation is satisfied by the input elements that you sample. So it's like a probabilistic argument, where here it's a reduction-based model. So you ask algorithmic questions. So you have to, you have the linear relation, or it's a relation of a higher degree if you work over groups with k-linear maps, and you somehow have to find the roots of this polynomial. You have to switch to a univariate polynomial somehow, and then find the roots of this polynomial. So you have this additional step that you need somehow to move from multivariate polynomials to univariate polynomials, and there are all kinds of ways to do that. And in addition, you have the limitation that all of our results and all of the results of Buxbauer et al. Are for groups of prime order, right? Because you need to work over a field because you want to find the roots of the polynomial. And it's interesting whether or not something can be done for groups of composite order as well.
But you do get exact security results, right? For group of prime order, you get like exact security results also, or like in generic group model, like.
So we get reductions, right? So you get reductions. So you get a reduction. Let's say yes, a concrete a reduction with concrete parameters from let's say CDH to discrete log, or from DDH to discrete log.
Got it.
Yeah.
Okay. Any more questions? Okay, so if we have no more questions, then thanks again, and we'll move to the next talk. It will be on lower bounds on time memory trade-off of function inversion. And Dror will give the talk.
Hello, everyone. I'm Dror Chawin from Tel Aviv University. Hello, wherever you are right now. This is joint work with Iftach Heitner and Noam Azor. Let's start by describing the problem. Wait, my computer is stuck. Okay. So function inversion. Basically, we have a function f and an image of the function y, and we wish to find x in the preimage of f. To do so, we have Oracle access to f, as well as some side information on f. We can think about this in actually in two stages, like a pre-processing stage, which outputs an advice string A, the side information, and then the decoding phase, the online phase, which is given y, which we wish to invert. Then using queries to f, it must find, hopefully, a preimage for f, for y over f. And we usually want this to work with high probability over random choice of f and y. F is usually chosen uniformly at random from the set of functions from n to n, while y is an image of uniformly chosen input x. And we don't have any bounds on the algorithms involved, except for the space requirement. This is the length of the device. And q, which is the number of queries. These are effective lower bounds on the space and time required for inversion. And these are the parameters we are interested in. And there's another variation, which is non-adaptive. The variant I just mentioned, you can ask the queries one by one, and by the result, you can decide the next query. And here it's impossible. We model this by adding an intermediary stage query selector, which has to select at once all of the queries. And then in the decoding stage, the online, the inversion stage, we have the advice string and the y, which we wish to invert, and the results of the queries. And there's no two-way communication here. And again, we wish to find the preimage for y. And any non-adaptive algorithm may also be, I guess, it can be formulated as an adaptive algorithm. Therefore, any upper bound on non-adaptive inversion also applies to adaptive inversion. And likewise, lower bounds on adaptive inversion naturally extend to the non-adaptive case. This problem is interesting because, first of all, many crypto systems which we're actually using in practice, their security analysis hinges on the fact that, on the assumption that the underlying hash function or cipher function is ideal. Basically, it behaves like a random function, and this setting captures this exactly. Next, we also have black box separation. Assuming that we have that one-way functions exist, this problem captures exactly what we can or cannot do. And also, it has been recently shown that any new interesting lower bounds on non-adaptive inversion also imply groundbreaking Boolean circuit lower bounds. And let's cover for a moment the known upper and lower bounds. For upper bounds, we have the trivial inverters, which could be either adaptive or non-adaptive. For example, I can just query the entire function until I find a good preimage for y. I can also not use any queries and just keep an entire description of f in memory, which is also huge. And I can also do like a combination of both, but this is not very interesting because these requirements are too big. For adaptive inverters, we have the algorithm first described by Martin Hellman, which allows for both time and space to be sublinear in n. And it is particularly useful for permutations in particular. And it is used in practice, actually. And for non-adaptive inverters, interestingly, nothing is known, no upper bound. So I will be really curious to hear if you can think up of one. And for lower bounds, there's only one relevant lower bound for us, which has been presented by Yao. And it applies to both adaptive as well as non-adaptive inversion. For the adaptive case, there is still a gap, though for permutations, it is completely bridged. While for the non-adaptive inversion, there's a huge gap. And of course, one reason for that is exactly the aforementioned paper, which shows that improving it will imply new circuit lower bounds. Our results are threefold. Every time we took an inverter, an inversion algorithm, and we posed an extra constraint on one of the phases, and we proved a lower bound for that case. So our first result pertains to adaptive inverters with linear advice. We model this as two parts, a preprocessor and a decoder phase. And we also require the algorithm to have high success probability. Basically means that it succeeds with a constant probability. The half here is not really important. And what is linear advice? I say that it has linear advice or linear preprocessing if given the advice strings of two functions, any two functions, f and g, I can easily compute the advice of the sum of the function f plus g. Now, this sum between f and g could be any coordinate-wise operation. And actually, the sum on the right doesn't have to be addition, it could be any operation, as long as the left-hand side is computable from the two elements on the right-hand side. And for this case, an adaptive algorithm with high success probability and linear advice, either the advice, the length of the advice, or the number of queries must be at least order of n over log n, which pretty much bridges the gap. And we also have a more general version of this theorem in the paper, which allows for other ways to compute the advice of the sum from the individual advices. And this is the first result. The second result is for non-adaptive inverters. Here we give the constraint on the decoding phase, the last stage, which receives the queries and the advice string and wishes to invert. Here we have an affine decoder. That is for any fixed values of y, which is the image we wish to invert, and a, the advice string. It behaves, it outputs exactly an affine function of f. F here is treated as a vector. And in this case, and with the added caveat that the size of the underlying field should be exactly n, we prove that the advice must be at least linear in n, which also basically bridges the gap. Now, by itself, this is not a very strong model. It can't do much. It can't even use its own queries very efficiently. But we use it as a stepping stone for the next proof on stronger inverters, which are more flexible. And this is this one. It is the same premise, but here the decoder is an affine decision tree. Here it means that for fixed values of y and a, it behaves exactly like a decision tree. A decision tree as shown here below, where the path is determined by results of affine functions of f. So the tree and the alphas and the betas are functions of y and a, but the path is dependent on f. And we also require that all of these alphas, they use no more than q different values of f. We just use this representation because it's cleaner. Now, this is interesting because it allows for a spectrum of complexity of this decoder. When the depth of the tree is 1, then this reduces to the previous case, which is very weak. But if I increase it just to 2, which is still very low, this is enough to compute multiplication of values of f and to do pointer jump. For example, I read the queries and I use one query to point to the value of another query and I output that result. If I set the depth of the tree to equal to q, the number of queries, then this could model any possible, like the general case of non-adaptive inverter, which is the most powerful. And so here we also have a lower bound on the advice, and to make it simpler, it means that when the queries are linear in n, then S, the advice is order of n over d log n, and when q is sublinear in n, the advice is order of n over d, depth of the tree. And when d equals to q, which is the strongest general case, this matches Yao, which unfortunately still doesn't improve, but this does yield a nice lower bound on many useful decoders, many which are not like or most complex imaginable. And yes, this is basically it. So thank you very much, and yeah, if you have some questions, I'll be happy to answer.
Okay, so thanks a lot for the talk. I'll start with a quick question. So your work looked at all kinds of classes, limited classes of advice and decoders, etc. Right? So were there any previous works that tried to make some kind of look at some kind of special cases and that also got some results, or is it like the first one?
Well, no, not really. There's been a lot of work on, especially on the adaptive variant of the problem. We actually focused on the non-adaptive. The adaptive proof is simpler and cleaner, and most of the work was on upper bounds. Now there are some lower bounds, but they don't really use. There is one lower bound which by Shamir et al. Which is a generalization of all Hellman kind algorithms. So they used a kind of graph argument to include a huge family of algorithms, and they proved that the lower bound in this case, the upper bound or the lower bound cannot be improved. I don't recall at the moment. And some papers also showed for other settings that that maybe some algorithm work or don't work for a fraction of functions, but here we really also treat f as a random function.
I see, kind of a structure, right? And the advice or decoding are kind of structured.
I don't recall seeing anything for the advice, though I do know there is a new paper about this problem with quantum advice. Yeah.
Yeah. Okay. So seems like an interesting direction.
Thank you.
Okay. Thank you.
There is also a question by Lior saying, do your lower bounds hold also if there is a shared randomness between pre-processing and the online algorithms, like the Hellman attack?
Does it hold if we have shared randomness between the pre-processing and the decoding?
The online algorithms, yeah, particularly.
And the online, yes, and the online stage. We really didn't consider it, so I can just see if something pops up. I believe they should hold because for example the random string could be hard coded in a certain sense. At least you can hard code a really long string into both. It's not the same as having a random string, but since the random string could be independent of f anyway, then for such an algorithm to work, it must work for most random shared randomness. So even for a fixed one, it should at least do good work. So our lower bound does hold for any fixed previous information which is independent on f. So I believe it could still apply for the case of shared randomness.
Thanks for the talk.
Thank you very much.
Thanks for the talk. So let's move to the next one. It's titled Superlinear Time Memory Trade-offs for Symmetric Encryption. And Xiao will give the talk. Shihu, sorry.
Yeah, no problem. Thanks. So, is the slide looking good?
Yes.
Oh, great. Okay. Yeah. Thanks, Anat, for introduction. And I'm going to talk about. I'm going to talk about time memory trade-offs in symmetric cryptography. I'm Shihu, and this is joint work with Wei Dai and Stefano Tessaro. Classically, security proofs gives upper bounds of advantage for the adversaries in breaking the scheme. These upper bounds are expressed in terms of the time complexity T and the query complexity Q. In this work, we target concrete security. We would like this bound to be as precise as possible. However, the memory complexity is another important factor that affects the feasibility of an attack. In fact, many cryptanalytic attacks achieve time memory trade-offs. Here, we consider proving upper bound on the advantage that additionally depend on the memory of the adversary. But this is not very easy, and only recently we have seen progress in a memory bounded setting. Taking the randomized counter mode encryption as an example, the classical textbook security theorem ignores the memory complexity of the adversary. The information theoretic term in the bound is the probability that there exist two encryption queries that use the same R. However, by turning this into an attack, it causes memory to remember these R's. And therefore, we would like to see how the bound changes if we consider the memory of the adversary. Such a bound was only recently proved by Jaeger and Tessero, and subsequently improved by Deneuer. For this bound, the information theoretic term implies that there exists a time-memory trade-off, because the smaller the memory, the more messages we need to encrypt to distinguish. Actually, proving this result is quite involved, and to show the tightest possible bound, we need to use techniques from communication complexity. Of course, this is about one specific construction. The question we ask in this work is, what is the highest security a construction can achieve in terms of the number of messages that can securely be encrypted in a bounded memory setting? Even further, can we obtain a trade-off that permits Q to be larger than big N for small memory, where big N is the domain size of the underlying PRF? Note that Q larger than big N is impossible to achieve via standard techniques without bounded memory. This is interesting because it will allow us to reduce the domain size of our underlying PRF while still securely encrypting a large number of messages. A bit more precisely, the main contribution of this paper is to study the security of two natural symmetric encryption schemes in the memory bounded setting. The first scheme is the sample then extract scheme proposed by Tessero and Theoretic, and the second scheme is the K-XOR scheme by Bernard, Godrich, and Krafzik. Both schemes depend on a parameter K, which corresponds to a number of clocks to the underlying PRF, and achieve better and better security as K increases. In both settings, the trade-off admits Q to be larger than big N for small memory bound S, and sufficiently large K. In order to analyze the constructions, we use a number of techniques, some of which are novel. For example, the proof of STE relies on tighter hybrids via KL divergence, and the novel use of a decomposition lemma by Goose et al. For K-XOR, we leverage a connection between the security of K-XOR construction and the next decoding of the K-XOR codes. In particular, we use higher moment method to show a new and tighter combinatorial next decoding bound for the K-XOR code, which is of independent interest. Previously, the bound on STE is suboptimal. It proves that Q can be larger than big N if given the number of calls to the underlying PRF is at least log N, even for a very small memory bound. For the K-XOR, the previous analysis already proves good security bound without considering the memory, but little was known about the K-XOR in the memory bounded setting. In the remaining time, I will introduce the constructions of ST and K-XOR. Both schemes can be regarded as a generalization of the randomized counter-mode encryption. We start with construction of the ST scheme. First, instead of sampling one random R, we sample K random values R1 to Rk. Then we evaluate all K values in the function f, concatenate the results, and apply an extractor to obtain a mask for the plaintext. The ciphertext is composed of the R1 to Rk, the seed of the extractor, and the mask plaintext. Here, specifically, to get a desired bound, we choose a two-universal hash function as the extractor. The K-XOR construction is slightly different from the ST construction. Here, the K-XOR construction XORs the PRF outputs as a plaintext mask, instead of applying an extractor to concatenation of the PRF outputs. Though we gave the trade-off analysis for both ST and K-XOR constructions, a few problems regarding these two constructions are open. First, we still don't know whether the trade-off bound for ST is tight or not, even though aesthetically it looks optimal. For K-XOR, we also provide several attacks and show that the trade-off is tight for very small memory case. However, it is interesting to examine whether the trade-off is tight for general memory and whether we can improve memory so that it matches the BG case bound in the Q smaller than big N case. The full version of our paper can be found on the ePrint. And thank you, and I'm happy to take any questions.
Thank you. And do we have any questions? You can just speak up if you'd like to ask something.
Just a question slash clarification that the notion of time memory trade-off in the last two talks, I think were different. Yeah. So if I'm getting it wrong, please clarify. In this talk, it was memory as like space complexity. In the previous talk, it was memory as in advice.
Right. Yeah. In previous talk, it's just
to make sure I got
it. For here, we're just turning machines memory bound.
Just because you commented on it, yes, but the advice is actually an effective lower bound on the space complexity of the inversion. So there is basically the same.
Sure. Thank you.
Thank you. Okay. Any more questions? Okay. So if we have no more questions, so thanks again. And let us move to the last talk of the session on expected time cryptography, generic techniques and applications to concrete. The chat, yes, to concrete soundness. Okay, and Joseph will give the talk.
Okay. Hi everyone.
Hi.
Oh. Sorry, just a sec. Okay. Hi, everyone. I'm Joseph, and I'm going to talk to you about some joint work I did with Stefano Tesoro. In this work, we provide techniques for giving concrete security bounds for expected time adversaries in information theoretic settings. Then we applied these results to proving the soundness of some proof systems. Let's start by recalling the purpose of concrete security. Broadly speaking, we define security notions by advantage functions, which map a scheme pi and an adversary A to a number between 0 and 1, representing how successful the adversary is in breaching the security of pi. In the typical asymptotic formalism of security, security is a binary property. Schemes and attackers are parameterized by a security parameter, lambda, and a scheme is considered secure if all polynomial time attackers have negligible advantage. This formulation doesn't provide any guarantees when we actually instantiate a scheme, thereby fixing the security parameter. This limitation is addressed by using concrete security. Here, a scheme is fixed, and we quantitatively bound the advantage of attackers as a function of the resources they use. By estimating the resources that attackers have, we gain a more precise understanding of how secure a scheme is. Given a concrete advantage bound, we can refer to the resources needed to achieve advantage 1 as the security level of a scheme. The most commonly considered resources is the worst case computation time of an attacker. As an example, for collision resistance of a hash function that's modeled as a random oracle, standard analysis bounds the advantage with a birthday bound. In this work, we'll consider proving bound when we instead know the average case runtime of the attacker. This is a natural measure which commonly arises in cryptanalysis and certain types of security proofs based on simulators or extractors. Unfortunately, many of our common analysis techniques fail in this setting. As a first attempt for our collision resistance example, we can derive bounds by bounding the probability an attacker makes more than little q queries plus its advantage with at most that many queries. Applying Markov's inequality to the former term gives a bound, the cube root of the expected runtime squared over 2 to the output length. On a positive note, This is a very generic proof technique. For any worst case bound of q to the d over n, we can use it to obtain an expected time bound that's the dth root of that, essentially. This suffices for asymptotic analysis and preserves the security level of the scheme, whether we're looking at worst case or average case runtime. However, this d+1th root is not tight, which will mean that it can give the incorrect security level when this is embedded in some higher level analysis. Our goal in this work was to provide techniques for extending existing worst case analysis to prove tight expected time bounds. The general form of the result looks similar, but should obtain a dth root rather than a d+1th root. We have the same benefits as the Markov-based analysis, but now must assume that the existing proofs had particular forms, and we can show that this bound is tight. This is done by giving a matching attack. In particular, if we have a matching worst case attack, then we can design an adversary which flips a biased coin and uses the result to either abort immediately or run the worst case attack. Simple analysis gives that this expected time attack is tight with our new bounds. So for example, with our collision resistance example, the square root of a birthday bound is the correct bound. Broadly speaking, the contributions of our paper were twofold. First, we provided these generic techniques for bounding advantage based on expected runtime. These extended either bad flag analysis techniques for identical until bad games, or the pointwise proximity technique, which is a special case of the H coefficient method. Both of these give this relationship between worst case and average case advantage we've been discussing. Some example applications we showed include the collision resistance and PRF security in the random oracle model, and discrete log security in the generic group model. As a particular instantiation, we applied our tools to give concrete analysis for the soundness of proof systems. This was based on a Boodle et al. Framework for multi-round public coin protocols, which uses an expected time forking lemma. As a particular instantiation, we gave the first quantitative bound on the soundness of the bulletproof proof system. In the generic group model, this bound upper bounds the probability that a cheating prover can convince a verifier of a statement by the probability that a related attacker can find a witness for that statement, plus a quantity related to the number of group operations performed by the prover and the sizes of the circuit defining the relation and the group being used. Unfortunately, the bound we were able to prove gives a security level which is fairly low for modest-sized circuits. So it would be good to understand if an alternative proof flow could give a better bound. Ghoshal and Tesaro gave a partial answer here by giving better bound in a recent ePrint paper, though they do so by proving things directly in ideal models, whereas our results came from plugging in our average case generic group model bounds for discrete log security in at the end of a standard model proof flow, reducing things to discrete log security. With that, I've reached the end of my talk. Thanks for listening.
Thanks for the talk. Are there any questions?
There is a question by Michael. Is there hope for extending this to the computational setting? I would amend by saying at least in the reduction setting, like where we do not necessarily want to prove unconditional bounds.
Right. So our techniques can kind of compose nicely if you have a proof which is kind of partially reductions and partially information theoretic analysis. But it's not clear that we can directly use it for the reduction part of the proof. And really, yeah, techniques are very much kind of able to deal with giving specific bounds when we're looking at something information theoretic, whether in a ideal model, or if you're looking at, say, bounding the probability that some random strings collide with each other. Things like that, we can apply our results to.
Do you think the results of Uli and David in the first talk might be extended to maybe expected time attackers to some extent, and that conceivably could simplify things? Or this is like, you think, inherently for worst or like deterministic attackers maybe? Because they put like the bad event at the beginning. It seems like it might be helpful here, but I'm not sure. Maybe it's fundamentally inapplicable.
That would be interesting to look at. I'm going to be just kind of guessing here. I haven't looked at it closely. My initial impression is that they might be fundamentally incomparable, because one kind of thing you have to be careful with in this expected time setting is that we can no longer assume our attackers are deterministic. The fact that they run an expected time might be determined based on their internal coins. So trying to fix the worst case coins then would change their runtime. So this could potentially cause issues, but again, I haven't looked at it in detail. So that would be something interesting to consider.
Yeah, it doesn't look like this. These roots can naturally come up in that kind of analysis. So I agree with you, but worth maybe checking to be sure.
Any other questions? Yeah. Thanks, Joseph, for the joint presentation. Your colleagues had some comment there. I don't know if you got it seriously or not. It was an interesting presentation with the pet trying to help you. We have a few minutes with potentially questions that apply to any of the talks of the session, in case there is any. You don't have to necessarily use this time. And before that, I thank again all the speakers of the session and the authors and everybody who attended.
Thanks, everyone.
And
it's a nice session. Yes, so if there are any more questions.
Yeah, if there is not other questions, I think we have a break, and then the secret sharing and coding session starts in about 40 minutes from now.
Right.
41 or yeah. Thank you, everyone, and see hopefully most of you there.
My apologies. I was not looking at the screen. So we're going to go into breakout rooms if you would like a social break. Let me get those started now.